So section 5.1 is going to talk about probability distributions. We're also going to talk about the mean, which is also the expected value, and standard deviations surrounding probability distributions. Well, let's just remind ourselves about a few things here in terms of probabilities and things like that. One of the things I have on your handouts is something that you should recall about probabilities. What's this stuff right here meaning to say? I didn't take out math type to type this in, but what's it getting at in terms of probabilities?
0.
Probabilities are between 0 and 1. Something that has a probability of 1 will happen, probability of 0 cannot happen. And within probabilities, we can look at random variables. Now there's going to be different types of random variables, but our random variables all have to have the same common characteristics, is that they are a single numerical value. It could be continuous, it could be discrete, but it has to be a numerical value. It has to be a number in order for it to be a random variable. So let's take a look at a few different random variables here. We could look at something that might be a discrete random variable. We could look at something that would be a continuous random variable, or something that might not be a random variable at all. So that's going to be our example A. And I'm just going to number these out of convenience, so I don't have to squeeze in too much here. 1, 2, and 3. So we want to determine whether or not these different events are random variables, and if so, what kind of random variable. Let's start by looking at the number of points scored during a basketball game. Now, discrete random variable means that our choices are just definite numbers, nothing in between. So for instance, in a basketball, can you score like a fraction of a point?
No.
No, you can't. So your scores are like 0, 1, 2, 3, all the way up to, I think the Detroit Pistons took part in the highest scoring NBA game ever during regulation. It was like 163 points. They beat the Denver Nuggets. Anyways, that's a discrete random variable, the number of points you score. So that would be a 1. How about the time that it takes to fly from, say, Detroit to Chicago, one city to the next? Omar?
2.
2. Yeah, time could be anything in some interval. So from 0 to whatever. Hopefully not terribly long if you're going just from Detroit to Chicago. The eye color of the people on that flight from Detroit to Chicago. What kind of random variable is that? Or not. Yeah, or not. It's not. Tahara, how come it's not a random variable?
Because it says it has to be a single numerical value.
Exactly. These aren't numerical values, so they're not random variables. The time that it takes a light bulb to burn out. I never seem to get the 10,000 hours that says on the package. I'm like, whatever. But the time that it takes for a light bulb to burn out. Hermione?
Continuous?
Yeah, it's continuous. It's not discrete because it can take on any value in some interval. So that would be continuous. Good job. The number of students, statistics students now reading a book. Yeah, 1. So number of students is a discrete random variable. And last but not least, the number of free throw attempts before the first shot is made. How many times you got to sit there at the line before you rip the cords? That's going to be a discrete random variable. Nice. Now within this framework, a lot of times you'll have an experiment. These could be the outcomes of your experiment. Here are the associated probabilities of that experiment. If this is going to be what's called a probability distribution, then the sum of these probabilities has to be 1. This has to total up to 1, meaning it's certain that something will happen that's in here. So this is where we're going to switch over to Google Sheets. Take a look and see if some of that sums up to 1. So that's example A here. And that's actually already put in here for you. My bad, I didn't mean to do that. If you had to do that for yourself, you would hit equals and then sum, and it's suggesting something, and it works good for me. B2 to B7, and that total is 1. So yeah, this is a probability distribution. This is a nice valid way to describe what could happen. Now, if I give you something that doesn't total to 1, it's not going to be like 1.0001 or 0.999. I mean, those feel like rounding errors. If it's something that's not going to be a distribution, it's going to be total to something far enough away from 1 that you won't think it's a rounding error. Let's move down to this next example because I think some of the next concepts are going to be easier to be understood if we talk about something that's a little bit more tangible. Rolling dice. We're going to roll 2 dice and look at the total. How many different combinations, how many different possibilities are there in this experiment? If you roll 2 dice, how many different possible outcomes are there?
36.
36, good. So you've got 6 times 6 is 36 possible outcomes. And of those possible outcomes, there's only one of them that represents rolling a 2. Hence, the probability of rolling a 2 is 1 out of 36, or the decimal value is this. Okay. And then you could look at the probability of rolling a 3. How many ways are there to roll a 3 with the pair of dice?
2.
2. Right there. So that's 2 out of 36, and that's our numerical value there, and so on. You could keep going, and I'll only do one more because I'm running low on colors. So 4 out of 36, etc. A good question would be, well, what's the average roll? And when you're dealing with probabilities, you can actually calculate this if you have a distribution, either a continuous or a discrete distribution. But we can calculate the average, and that average is exactly what you think. So I'll write the Greek letter in our alphabet, mu, which is exactly the mean. The way you calculate the mean is you take and add up this product, x times p of x. The value times its probability, and you add it up. That also goes by another name. It's called the expected value. This is what you would expect if you did this kind of experiment hundreds and hundreds of times. What's the average roll of a pair of dice? That's a good question. So, all right, let's do that for this one up here, this set of data. And let's see, so click over to example C here. And in column E, I want to calculate this column. I want to calculate x times p of x and see what I get. All right. So if I'm going to do any calculation, James, how do my Google Sheets commands always start out?
Equal sign.
Equal sign. Perfect. Equals. And I want x, which is in column A, so I'll click that, times, so shift and then 8, and then column D, because that's where the associated probability is. Now, I did show you some of this other stuff. That's just so you can see this. What's in column D is the actual decimal value of 1 over 36. Now, when I press the Enter key, I think it's going to ask me, oh, do you want to do this for the rest of the column here? And yeah, sure. You want to autofill that for me? Great. If not, you can always click and drag this little circle, drag it down, and it should copy that formula all the way down. So that's your x times p of x. But what I needed was the sum of that. So just a reminder, I think I've said it before, that stands for sum. It's a Greek letter S, it's called sigma, but you're summing that all up. What do you get when you sum that up? What's the average roll of a pair of dice? What are you getting? Jordan, did you get a number there? Got to vote for 7? You should be getting a 7. That one's already built in, so if you do x times p of x, should total up to 7. What this is saying is if you were at the casino, at the craps table, rolling dice, all evening, that if you've gone through hundreds and hundreds of rolls, your average roll is going to be 7. Now, it doesn't have to be a number that you can actually get. If you're rolling a single die, the average roll would be 3.5. And of course, you can't roll 3.5 with one die, but that would be your average roll nonetheless. All right. Are you able to get 7 out of this probability distribution? Hermione, was that a yes?
Yes.
All right, thank you. Let's go back and do that for example A. Try and find the average for this distribution. And I don't have a nice application for it like I do the previous one. Try and find that expected value. All right. So if I'm going to mimic that calculation, it should be equals here. And then I want this times, which is the 8, shift 8, and then the second column, which is this one. So A2 times B2. Autofill? Sure. And at the bottom, I've already got this set up so that it'll do the sum for you. You're going to have to do that yourself when you're working these things for yourself at home. Let's make that a little bit bigger. And one more. All right. There we go. So you should be getting about 0.397. That's the average value here, right? Was that one of the possibilities of a random variable is 0.397? No. A random value can take on those values. So our average value is not even something you could get out of this probability distribution, but that is the average value nonetheless. Now we're going to do something more with the average here, which is we're going to find the variance and standard deviation. Those mean exactly the same thing here that they did back in chapter 3 when we were working with variance and standard deviation back there. So how do you calculate the variance now? Well, it's a good question. Let me share it with you. So let's see, our variance, and this isn't working out too good. Let me try a different one. Our variance is going to be the sum of P of x, which is your probability, times x minus the mean squared. That's the formula for your variance. But we don't use variance too much. It does have some uses that we will take advantage of later on, but a lot of times we use a standard deviation. How do I get from one to the other? Yeah. So I'm going to take the square root of that, and that's going to give me the standard deviation. And here, mu is your mean. This is a little bit more of a painful calculation, which is why we're going to do it on Google Sheets. So on your next exam, you can expect to use Google Sheets on your exam. Now, I'm going to give you the commands that you might need for things like factorial and permutations and stuff like that, but you are going to have a little bit of skill with Google Sheets. Let's take a look at what that's going to look like here. So here's the formula I need to type in. I need P of x times x minus mu squared. So all your Google Sheets commands start out with equals. P of x, that's column B. Need to hit the times key, so that's shift 8. And then a parenthesis. Where should I go for my x?
A.
Column A. Minus mu. Now, unless you want to get really technical about how spreadsheets and stuff like that works, do yourself a favor. Literally just type in the number 0.397. In fact, you don't even need to type in the 0 if you don't want. You just type in 0.397. But you want to type that in, because that number is going to stay the same throughout this calculation. Then I want it squared. So I need that little up arrow key. Where do you find that up arrow key on your keyboard?
6.
Shift 6. So I want that squared like this. So here's what your calculation should look like. And let me zoom in a little bit so you can see it a little bit better. So it should be B2 times parenthesis A2 minus 0.397 squared. When you hit the enter key, like before, it should ask you, all right, do you want to do this all the way down? And the answer is yes. So, all right, let's see. It's enter. Do you want to do it all the way down? Sure, do my work for me. I appreciate that. Thank you. So, great. Those are all those numbers. Except I need the total of those numbers. So that total is going to be your variance. That's your variance. But a lot of times I'm not interested in the variance. What I want is the standard deviation. So, okay. How do I go from the variance to the standard deviation? How did I get from here to here, which is already filled in for you? Square root. And if you take a look at the command, it's just SQRT, square root. Square root of what? Oh, square root of that previous number. And if you click these formulas, it'll show you what cells are active in the calculation of that formula. So you can kind of double check yourself.
How many digits would you want?
You know, I'd probably, if I'm worried about a specific number of digits, I'll tell you. When we're dealing with probabilities, I usually like 4. But expected values, I don't know. You know, maybe 3, 2 or 3 at least. Yeah, good question. You might remember from your last test that we had some stuff that was significantly high and significantly low. What determined if it was significantly high or significantly low? Anyone remember? How do we define those lines that separated significantly high from significantly low? Right? It was with the standard deviation. How far away in terms of standard deviations did you have to be in one of those areas? Significantly high or significantly low?
2.
Yeah, if it was more than 2 standard deviations. So to find out what's unusual for a probability distribution, we can calculate the same thing. And you know, this is kind of like the problem with me doing Google Sheets. A lot of times I forget to change these numbers in the morning or erase them from when you guys do them. But that's exactly what I did. I took our mean, which is 0.397, and I subtracted 2 times the standard deviation. And I do that, and I get negative 0.82. All right. And I do 2 plus the standard deviation, and I get 1.61. So, okay. Let's put all those possibilities on a number line, and then take kind of a look at them real quick. So I got numbers 0 through 5. Those are my possibilities. Let's squeeze that in here. So 0, 1, 2, 3, 4, 5. Okay. Zero, 1, 2, 3, 4, 5. Let's look at what I got when I calculated that range of 2 standard deviations below and 2 standard deviations above. So I got negative 0.82 to 1.61, I'll call it 1.62. So it's telling me where my unusual values start. So it's going to be here to here. Now, unusual would be anything less than 0.82. Well, in this experiment, can I get anything less than 0.82? The only values I can get from this experiment are 0, 1, 2, 3, 4, 5. So these are going to be your typical values. How about 2, 3, 4, or 5? What is this saying about 2, 3, 4, and 5? These are your unusually high values. I mean, on average, you expect about 0.4. Anything 2 or above is going to be unusually high. You can't get anything that's unusually low in this case. We're going to repeat this with our dice rolling example. So we're going to go back and repeat that in just a minute. But for now, yeah, it's weird that you get this number that you can't really get out of this experiment, but that's okay. All it's saying is that these are your unusually high numbers right here. Those are unusually high. And there's nothing that's unusually low because there's nothing below that number, negative 0.82. So that's it. Numbers 2 through 5 are unusual. Let's repeat that for our dice rolling example. So let's go back to our Google Sheets, example C. We need to calculate the standard deviation next. So what you need to do is you need to fill in this formula here. You want P of X times X minus mu squared. So try and fill it in. What was the value for mu in this particular data set, this particular probability distribution? 7. That was your average roll. That's your expected value. So if you're doing this again and again and again, on average, you would expect a 7. So try and fill that in. If you're watching this later, maybe pause the video and try and fill it in. And then when you're done and want to check it, press fast forward past the pause button. I'm going to walk around and try and help out.
X.
Oh,
That's the calculation, but what's the standard deviation? Should be X. So P of X should be D. P of X should be column B. Yeah. So you need, first of all, you need the probability on the outside. You, it's not it's not worth learning on that. I mean, I can show you, but it's not worth learning on the calculator. So, and I got the formula here, you just gotta pick the right column. So if that's your P, that's your X. P of X, you want to pick from D, not from C. P of X. Let's see. Where you find these from column X? Yeah. Where you find the X? What column X? It's P of X. See, that's probability. X. It's only minus the mean. How are we doing over here? Cool. Good. Yeah, let's see what. Put this up here. Okay, yeah, you got X times this, we need P of X, so the outside term has to be column D, you did column A.
Okay.
So you just, if you make that a D4, then you need to copy it all the way down. It should work. Okay. Oh, you got the wrong mean. 0.397 was the mean for the last problem. It's 7 in this problem. Should be P-Rex. You don't want to type that, you want it should be cell D4. You shouldn't have the actual number, it should just be D4. And that way, it'll keep on updating all the way down the formula.
All right, so let's see here. The way this should look would be you want P of X times X minus mu squared. So equals P of X is in column D, asterisk for times, parenthesis X, which is in column A, minus mu. Now you have to type in mu, the actual number, unless you want to get really fancy with Excel or Google Sheets. So I'll click there. Do you want to do this all the way down? Yeah, please do. When you add that up, you get the variance. To go from the variance to the standard deviation, you want to take the square root. So it's going to look like that. Then, let's see what I want to do from there. Then I want to do the same thing I did before. I want to do 2 standard deviations above and 2 standard deviations below the mean. Since our mean is 7, that calculation is going to look like this. It's going to be 7 minus 2 times the standard deviation. I didn't actually type in the standard deviation, I just let Google Sheets handle that. I got from 2.17 to 11.83. So let's take a look at it numerically on handout. So 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So from 2.17 to 11.83. So these are your typical values. Typical. And I hate calling it like that. They're just not unusually high or unusually low. Are there any unusually high or unusually low values in this distribution? Well, 12 is outside that range. So 12 would be unusually high.
And then 2.
Great. Thank you, Matilda. And 2 would be unusually low. Unusually low. Nice. All right. We'll have to finish up some more next time, but we are going to continue to look with the expected values. One thing that you can think about is, for instance, why you'd have a negative expected value, say, in the game of roulette. What would a negative expected value mean is going to be happening with your bet? So, all right, we'll finish this up next time. See ya.